Every piece of software released, fully barring the software that runs on the Boeing 747 and things like that, has known bugs in it when it's released. And that's an acceptable trade-off, and it wouldn't be cost-effective for us to fix them all. Therefore, a tool looking for quality bugs with static analysis, it's very important that it have very low false positives, that it be very accurate. Because otherwise, if it's wasting the developer's time, then it's not contributing meaningfully because each bug that it finds is only worth so much. For security, it's critical that you avoid false negatives because it could be that one false negative that gets you on the cover of the Wall Street Journal. And in this case, the trade-offs towards minimizing false negatives is critical, even if you have to accept some false positives along the way. So let's talk about the implementation, or the inside of a static analysis tool a little bit. Most tools share these architectural components in common. They accept source code in the front end, they build some model of the program from that source code, and then they perform one or more types of analysis on it with some rules that tell it what to look for, security knowledge. And out the other end of this analysis, bringing the model together with the rules, comes a set of results that the auditor or developer needs to review. What are critical attributes of a static analysis tool? It needs to support the languages that your software is written in. And this seems like an obvious question, so if I've got a Java web application, my tool better support Java. But is your whole program Java? Probably not. You've got some XML configuration files, maybe you've got some PL/SQL stored procedures, JavaScript on the front end, maybe native C code. So the more of the languages your program is written in that your tool understands, the more complete your model will be, the better your analysis will be. Having the right analysis algorithms is also a critical attribute. Different techniques, and we'll talk about some later, are best suited to finding different kinds of bugs. It needs to be able to scan all the code you're interested in it scanning. This is an important one. This depends on the application, too. If you want the tool to scan code as you're writing it on the developer desktop, trade-offs here are very different from if you want to scan as part of a nightly build process, where maybe you've got 8 or 10 hours to complete a scan. Rule set is critical, both in terms of describing APIs so the tool understands what it's analyzing and determining what vulnerabilities you want to look for. And finally, and this one I think is overlooked too often, the results management system. So how do you present results to the user? How are they able to triage those and decide which ones to fix and which ones not to? Building a model. So this is the stage where you take source code and generate some sort of representation of it that you're going to perform your analysis on. Looks a lot like a compiler. You've got a parsing front end, and then you tokenize it, and then you probably an AST. Supporting one language and one compiler is pretty straightforward. Once you realize that you have to understand the same decisions the compiler is going to make, just as Microsoft C compiler and GCC interpret the code slightly differently, the static analysis tool needs to understand the different ways that code may be interpreted as well. So particularly in the C case, when you talk about embedded systems, you may end up supporting 10, 20, 30 different compilers, all for ostensibly the same language. You could bypass this by analyzing compiled code. So you could decompile the code, run some analysis on that, and then you would not have to guess what the compiler was going to do because you would have looked at the output of that to it. There's some problems with this. Decompilation is difficult. Anybody who's tried this, particularly for C, it's pretty difficult. The loss of context that you have when you're looking at the low-level representation is really critical, particularly when you're talking about security problems. Accessing a database and reading some data off the network look roughly the same at the machine code level. They're both network operations. But there are different security implications of that database access than there are for just simply writing out to a socket. And finally, we're doing all of this, building all these tools, investing in security because we want to fix bugs and make the software more secure. So eventually, you have to be able to map the problem you found back to the original source code so you can tell the developer what to fix. As I said before around capacity, there are trade-offs between what kind of analysis you want to perform, how broadly you want it to consider, how broad the scope you want it to consider in the software is, and how fast it's going to run. Tools that are going to run in real time as code is being written are not going to be able to do things like whole program analysis as the code is being written. So think about the trade-offs between a tool that you want to run in real time and a tool that you want to run overnight, and how broadly it can consider. And when I say scope, input travel through the program. Do I care about it in the context of this function that I'm writing, or this module of the program, or the entire program, or between multiple processes. Now, analysis techniques and rules are tightly tied to one another, so I'm going to talk about them actually at the same time. Probably the most straightforward, simplest analysis technique is one that we call structural analysis. This has to do with the structure of the program as it's declared, not possible execution paths or the way data moves between it, just the overall hierarchy of the structure of the program. An example of a bug you might want to find with structural analysis is this one here. I'm used to having a screen behind me to point at, so I'm sorry I keep pointing at my laptop screen. If you pass the same buffer into the first argument of realloc as you assign the return value of realloc to, you may have a memory leak if realloc fails. So if it can't allocate enough new memory, it's going to return an error code, and that's going to overwrite your remaining pointer to the memory that's already allocated. Now, the bottom of this rule is, the bottom of this slide is a structural rule designed to detect this vulnerability. And you can see it's pretty straightforward, and it corresponds pretty closely with the original source code. We say we're looking for a function call where the name is realloc, and it's part of an assignment statement, where the first argument to the function is the same as the thing being assigned to, the left-hand side of the assignment statement. Probably the most interesting kind of analysis, certainly the one that we hear the most about, is Dataflow or taint propagation. This is where we find most of the exploitable security bugs that we can find with static analysis. The idea is you're going to track where untrusted input enters the program, follow it as it's passed around between different variables and method calls and so on, and then identify points where it's misused or where it reaches an API that it shouldn't be passed to. Here we have an example of a command injection vulnerability with some made-up function names. So assume that get input from network reads untrusted input. So this is something that the tool needs to identify as a source of untrusted or tainted input. The rule at the bottom says the function we're looking for, and it says the post condition of a call to that function is that the return value is untrusted or tainted. Next, we come to what we call a pass-through. So this is a function that moves data from one variable to another. And in this case, we need to provide a mapping to the tool to tell it that if tainted data enters the second argument, then it's going to come out in the first argument. So if the second argument is tainted, then the post condition is that the first argument be tainted as well. And finally, we have what we call a sync rule. This corresponds to the kinds of vulnerabilities that you expect to find with Dataflow analysis. In this case, we say that if the first argument to exec is tainted, then it's a command injection vulnerability. The last kind of analysis and the last rule example I'll give is control flow analysis. And this has to do with paths of execution through the program and the order of operations. An example of a kind of vulnerability you might want to find with control flow analysis is a double free vulnerability. So in a C program, if you call free twice on the same memory allocation, then you can corrupt the program's memory hierarchy and potentially cause buffer overflows because the program may reallocate something that it's already allocated along those lines. In this code example, we've got a couple of paths. We have a couple of control structures, a while loop, a couple of if blocks. So you can imagine there are different paths one can follow through this code. The first one, the fairly boring one, is you don't enter the while loop, you don't enter the if block, you haven't executed anything interesting. Now, off to the left, we have a state machine representation of the rule that we're trying to enforce, which is don't ever call free twice on the same memory allocation. So if you think of the last state at the bottom as you found a vulnerability, and you think of the arrow at the top as where you begin, then you move between those states if and when the analyzer sees the statements that are on those arrows in between, the transitions. So we see we have a transition from the initial state into the freed state on a call to free with some variable x, and then we have a transition from freed to error when we have another call to free on that same variable x. So in this case, we just stay in the initial state. We haven't made any progress because we haven't seen any calls to free. The next scenario, we go into the while loop, so we see a call to free. Now, we've entered the first state, and we've bound x to the variable node in the program, because we saw a call to free on that variable. But we don't enter the bottom if block, and we don't see a second call, so no error here. Finally, you can probably see where this is going. We enter the while loop, we see the first call to free, we bind x to node, and then we enter the bottom if block, we see a second call to free on node. We see that there's a vulnerability, we enter that error state at the bottom and report something back to the user. The good thing about all this, it's kind of complicated, is that there are only two ways to go wrong, really. False positives